Okay, so we're being asked the wavelength of light changes from 520 nanometers to 478 nanometers when it passes into a liquid. What is the index of refraction for the liquid? What is the velocity of the light in the liquid? And again, because the information is not in the question, we're going to have to assume that the original medium was air, and therefore the refractive index of the original medium was 1.00. Okay, so this is another question about Snell's law, and in this case we can write down what we know. So what do we know? We know that the velocity in a medium is equal to the velocity of light divided by the refractive index for the particular medium. And we also know that the wavelength of light changes. Well, the velocity of light is equal to the wavelength times the frequency of light. When light enters a medium, the one thing that never changes is the frequency. So the frequency is constant. And the two things which do change are the wavelength and the velocity. So we're told that the wavelength of light changes, and therefore the velocity changes to compensate. So the constant is the frequency, so we will first calculate the frequency of the light, which will not change, and then, knowing that the wavelength changes, we will compute the new velocity. And from the new velocity, we will compute the refractive index. Okay, so let's do that conceptually and algebraically, and then see how much actual calculation we need to do. So let's have a look at our equation for the velocity. We are going to have two velocities. The initial velocity, which is equal to c, which is equal to lambda initial times the frequency, and we're going to have a final velocity not equal to c, which is equal to the final wavelength times the same frequency. So, expressing both of these in terms of frequency, I have the initial velocity divided by the wavelength is equal to f, and that is also equal to the final velocity divided by its corresponding wavelength. So I don't actually need to calculate the frequency. Now, I do need to remember that the refractive index is given by the velocity of light divided by the velocity in a medium. So, replacing the initial velocity with the velocity of light, and I have just removing the frequency, which we don't actually require, and therefore if I know the final velocity, then I could use the expression Vf is equal to c over nf, where nf is the refractive index in the final medium. So rewriting this to give myself the final velocity, I multiply both sides by lambda initial. So final velocity is equal to c divided by the initial wavelength multiplied by the final wavelength, and that should have been an f there. Okay, and we also know that this is equal to the velocity of light divided by the refractive index that we need. Okay, so I'm just going to take this part and come up here. Then I can rewrite that, divide both sides by c, and I'm left with the final wavelength divided by the initial wavelength is equal to the velocity of light. No, it isn't. Is equal to 1 over the refractive index that I'm trying to calculate, and therefore multiply both sides by nf, divide both sides by lambda f, and multiply both sides by lambda I, which we could also say we take the reciprocal of both sides. And so I'm left with the refractive index that I'm asked to compute is actually the ratio of the wavelengths. It's 520 nanometers divided by 478 nanometers. And actually the units cancel, as they should, because refractive index has no dimensions, and therefore I'm left with a straight calculation to find that the refractive index is equal to 1.08. It's actually equal to 1.087, which rounds up to 1.09. So my final answer is the refractive index in the medium, and we're not told what it is other than the fact that it's a liquid, is 1.09, which I'll write a little bit better than that. 1.09, and making life equal for the poor guy who has to mark it, let's make sure it's possible to find that on the page. And we're done.